In this lecture, we will be discussing the resting membrane potential and how it develops. So to get started, we have to differentiate between what are called chemical and electrical driving forces. Let's start with chemical driving forces. What is a chemical driving force? A chemical driving force is really simple. It's just a diffusion gradient. Okay, so if there's a high concentration of anything that exists outside of the cell, let's say these are sodium ions. Okay, if there's a high concentration, which is true, let's say that there's a high concentration of sodium ions outside of the cell and a low concentration of sodium ions inside of the cell. Well, we know due to diffusion, sodium is going to want to move from a high concentration to a low concentration. It's going to want to move from outside of the cell to inside of the cell. This is sodium's chemical driving force. The chemical driving force is nothing more than a diffusion gradient. Molecules or ions are going to want to move from a high concentration to a low concentration, and that's their chemical driving force. If, let's say, this is true also, that there's a high concentration of potassium inside of the cell, and there's a low concentration of potassium outside of the cell. Okay. If we think about potassium's chemical driving force here, potassium is, via its chemical driving force, is going to want to go from inside of the cell to outside of the cell. It's going to want to move from a high concentration to a low concentration, which is a chemical driving force. With chemical driving forces, we're always just looking at the diffusion gradient. Where does the molecule want to move? It always wants to move from high to low. So chemical driving forces are simple, right? It's just a diffusion gradient. Electrical driving forces are not much more complicated, but a little bit. Okay, so what are electrical driving forces? Let's make this as real as possible again. On the inside of the cell, basically any cell in your body, there's going to be a higher concentration of negatively charged ions compared to positively charged ions. Okay. Higher concentration of negatively charged ions on the inside compared to positively charged ions. Again, those ions are going to be a combination of both atoms and molecules that have a negative charge and a positive charge. But overall, there's going to be a higher concentration of negatively charged ions than positively charged ions. And thus, the inside of the cell is going to have a negative charge to it. Again, I said that's going to vary dramatically how negative that is from one cell to the next. But to get started, you have to realize that a negative charge is going to come from the fact that on the inside of the cell there are more negatively charged ions than positively charged ions. Okay, so if the inside of the cell has a negative charge due to the fact that there are more negatively charged ions than positively charged ions, what that means is the cell is going to pull positively charged ions within the extracellular fluid towards the cell. Okay, what are positively charged? What's something that's a positively charged ion? Well, sodium ions, for example, are positively charged. Calcium ions are positively charged. Okay, so in this example, an electrical driving force is the tendency of some ion to be pulled in one direction due to that direction having a opposite charge. Okay, so let me give you an example. Okay, well, I've been giving you an example, but let me elaborate. The inside of this cell has a negative charge to it. What that means is because the inside is negative, that's going to pull sodium and calcium ions towards it. So what we would say is that the electrical driving force for sodium and calcium is to enter into the cell. Negatively charged cells are going to pull positively charged ions towards them, and those are electrical driving forces. The tendency for some ion that's positively charged to get pulled towards a negatively charged cell is an electrical driving force. And the opposite can be true too. So let's talk about that real fast. So I just told you that the cell is negatively charged. There are more negatively charged ions on the inside than positively charged ions on the inside. If the inside of the cell is negative, the outside of the cell has a slight positive charge. Again, it could be slight, could be significant, depends from one cell to the next. But if the inside is negative, then the outside has to be positive. All right. So let's pretend that there is some, negatively charged ion on the inside of the cell. Okay? That negatively charged ion on the inside of the cell is going to have an electrical driving force pulling it out of the cell. So we would say that the electrical driving force for whatever negatively charged ion this is to leave the cell, right? Because the outside of the cell has a slight positive charge. There's going to be comparatively a higher concentration of positively charged ions on the outside than negatively charged ions. Okay, so it's got a slight positive charge, and thus it's going to pull negatively charged ions on the inside of the cell out. Okay? So I'm just showing you the opposite of what we just talked about so that you can see, right, this can go in both directions. Electrical driving forces are nothing more than an ion's tendency to move in a particular, to get pulled in a particular direction, because again, that direction has the opposite charge of what that ion is.
The next step in understanding how the resting membrane potential develops involves discussing what are called equilibrium potentials. Equilibrium potentials involve isolating and looking at one specific ion and how the chemical and electrical driving forces will influence that ion's movement into or out of a cell. What can be used to calculate the equilibrium potential is the Nernst equation. The Nernst equation is a very easy calculation to do. In this lecture, we will not be going over the Nernst equation. What we will be doing is actually explaining on a functional level what the equilibrium potential is, not learning how to calculate it. Because, quite frankly, anybody can do that. We are specifically going to look at the equilibrium potentials for sodium and for potassium. We are actually looking at specifically neurons, the average neuron. So equilibrium potentials for specific ions will be different in different cells. And I just wanted to make that point before we got started. So for example, the equilibrium potential for potassium with regard to neurons might be negative 94 millivolts. But within another cell, it could be negative 70 millivolts. Ultimately, the way that it's determined is exactly the same. It's simply that the concentrations on the inside versus the outside is a little different between cells, and that then changes the equilibrium potential. But understanding exactly how it's established on a functional level is exactly the same from cell to cell, even if the end number is a little bit different. So let's go ahead and get started in discussing the equilibrium potentials for sodium and potassium. In order to be able to do that, we need to discuss how they would develop in the first place.
So to start off with regard to development, as a kind of membrane potential, this negative charge is going to develop. And this is going to be true for the current discussion of equilibrium potentials too. The inside of the cell has just as many negatively charged ions as it has positively charged ions. So the charge is neutral on the inside. The same is true for the outside. There's just as many negatively charged as there is positively charged ions on the outside. Okay, so the outside, the extracellular fluid, is neutral as well. All right. But there are different distributions of particular ions. For example, potassium is high on the inside and it's low on the outside. Sodium is high on the outside and it's low on the inside. So there does exist what are called, as you know, chemical driving forces. Okay? Potassium has a chemical driving force, a diffusion gradient, to want to leave. Sodium has a chemical driving force to want to come in. Right? So let me say this in a different way. There is no electrical driving force whatsoever to start with. Right? The same number of negatively and positively charged ions, total number, I'm saying total number here, the same total number of negatively charged and positively charged ions exists on the inside. And the total number of negatively charged and positively charged ions on the outside is the same. Okay? But that doesn't mean there can't be uneven distributions of particular ions on the inside and the outside. For example, potassium's higher on the inside than it is on the outside, and sodium is higher on the outside than it is on the inside. So there exists individual chemical driving forces to start off with, but there exists no electrical driving forces to start off with. Because again, if you looked at the inside and the outside of the cell, and you looked at there's lots of different ions, right? Many, many different types of ions. And if you looked at the total number of negative and positively charged ions on the inside, it would end up being the same. Same is true for the outside, but there are individual uneven distributions of particular ions, which creates and it results in their existing chemical driving forces, but no electrical driving forces. So what we will look at first is potassium. You know that potassium is high on the inside and it's low on the outside of the cell. So there's a chemical driving force for potassium to leave. But there exists no electrical driving force because the same total number of positive and negatively charged ions exists both on the inside and the outside. Okay, so there's a chemical driving force for potassium. And now what we need to do is we need to pretend that the plasma membrane has lots of pores, right? Integral proteins, transmembrane integral proteins, lots of pores for potassium. Okay, so there's actually a route for potassium ions to get out of the cell. There are these pores in the membrane. And these pores within the membrane only exist for potassium and for nothing else. Not for sodium, not for chloride, not for calcium, only for potassium. All right, so what's potassium going to do if you have this hypothetical cell that's very permeable, very leaky to potassium due to all these pores, these integral proteins? What's going to happen is potassium is going to leave through its chemical driving force. Of course, it has a chemical driving force to leave, and if we make the cell very leaky to potassium, then potassium is going to exit through its chemical driving force. But as potassium leaves, you have to think about what that's going to do to the inside and the outside, more particularly the inside. And what's happening to the inside? As potassium leaves through its chemical driving force, right? It's going from the inside to the outside. The inside of the cell is losing positively charged ions. Right? To start off with, it had the same number of positive and negatively charged ions on the inside, total number, but now it's losing positively charged potassium ions as the potassium ions leave through their chemical driving force. Okay, well, if the inside is losing these positively charged potassium ions, then what's going to happen is the concentration of negatively charged ions on the inside is going to rise compared to the number of positively charged ions on the inside, because the inside is losing these positively charged potassium ions, and the inside is going to begin to become negative. It's going to develop a negative electrical driving force. All right. So now what we need to do is think about what this negative electrical driving force, how that is going to influence the potassium ions, which are leaving through their chemical driving force right now. So you know the potassium ions are leaving through their chemical driving force to the outside of the cell, high to low, And the inside is losing these positively charged potassium ions, so the concentration of negatively charged ions to positively charged ions on the inside is rising, so the inside is becoming negative, and a negative electrical driving force is developing. Okay, so what do negative electrical driving forces do? They pull positively charged ions towards the cell. So what this really means is as the inside begins to become negative, it's going to pull the potassium ions back towards the cell. What this really means is it's going to begin to slow down the rate at which potassium leaves. Let me say this a different way. As potassium leaves through its chemical driving force and causes the inside of the cell to develop a negative electrical driving force, that negative electrical driving force is going to slow down the rate at which potassium can leave through its chemical driving force. As the electrical driving force becomes stronger, as the inside becomes more and more negative, that's going to continually decrease the rate at which potassium can leave through its chemical driving force, because the electrical driving force is going to pull the potassium ions backwards towards the cell. So where am I going with all of this? What we can do is we can measure the inside of the cell in this hypothetical situation, actually, because we can make this hypothetical situation real in a lab. And what we find out is that with regular intra and extracellular fluid, here's what's going to happen. If we allow the interior to hit negative 94 millivolts approximately, what's going to happen is we are going to get to potassium's equilibrium potential. What does an equilibrium potential actually mean? Well, at negative 94 millivolts, first of all, how do we actually get to negative 94 millivolts? Okay. As potassium leaves through its chemical driving force, the inside of the cell is going to become more and more negative as it continues to lose more and more positively charged potassium ions. And eventually, enough potassium ions leave to make the interior drop to negative 94 millivolts. You know, first it's going to go to negative 5, then negative 10, then negative 15, then negative 20, right? You get the point, I hope. As more potassium ions exit, the inside becomes more and more negative. And this negative electrical driving force begins to pull potassium ions backwards and slow down the rate that potassium ions can leave through their chemical driving forces. All right. So once we get to negative 94 millivolts, if we probe this cell and we measure it, at negative 94 millivolts, potassium is at its equilibrium potential. What that means is that there is no net flux of potassium at all. Okay, let's say that differently. At negative 94 millivolts, the drive for potassium to leave through its chemical driving force equals the drive for potassium to be pulled back through its negative electrical driving force. So the chemical driving force for potassium to leave equals the electrical driving force for potassium to come back. And at that point, again, there's no net flux of potassium out and, of course, into the cell. Right? The drive for potassium to leave equals the drive for potassium to come back. Right? The chemical and electrical driving forces are, in fact, the same once we get to an ion's equilibrium potential. In the case of potassium, we just get stuck at negative 94 millivolts. Why are we stuck at negative 94 millivolts? Because the drive for potassium to leave through its chemical driving force equals the drive for potassium to come back through its electrical driving force. So we no longer have any net, what would be efflux of potassium out of the cell. Right? Basically, there would be no potassium leaving and no potassium coming in at this point, right? Because the two driving, I mean, that's never going to be totally true, but these two driving forces equal one another, right? So the membrane potential isn't going to change anymore. It's just going to get stuck at negative 94 millivolts. If you wanted the inside to become any more negative, you would need potassium to keep leaving at a greater rate than it would be coming in, And that's not going to happen at negative 94 millivolts anymore because the drive for potassium to leave equals the drive for potassium to come back. So we're stuck at negative 94.
So we just finished looking at potassium's equilibrium potential with regard to the average neuron. And now we want to take a look at sodium's equilibrium potential with regard to the average neuron as well.
Now we're going to do this for sodium. To start off with, we know that the inside has just as many positive and negatively charged positively charged ions as it has negatively charged ions. And we know that's true for the outside too. There are just as many positive and negatively charged ions on the outside. Okay, so there's no electrical driving force to exist. Both the intra and extracellular fluid are neutral. All right, but what we do know is that there's a higher concentration of sodium ions on the outside than there is on the inside. So there does exist a chemical driving force for sodium to come in, and now we're going to pretend that the cell is very permeable or leaky to sodium. There are all of these transmembrane integral proteins which are pores for sodium ions. And if you have a cell, which again we can create a situation in the lab where this actually exists. If you have this cell that's only permeable to sodium, there's a whole bunch of sodium leak channels that exist in the membrane, then here's what's going to happen, right? Sodium, through its chemical driving force, is going to begin to come in through the leak channels. And now we want to think about what effect that's going to have. As sodium begins to enter into the cell through its chemical driving force, the inside of the cell is going to be gaining positively charged ions. So the proportion of positively charged ions on the inside compared to negatively charged ions on the inside is going to rise. So what does that mean for the inside of the cell? As the sodium ions begin to come in through their chemical driving force, the inside of the cell is going to begin to become positive. And what's going to happen to the outside of the cell? Well, the outside of the cell is losing positively charged ions, right, the extracellular fluid, because the sodium ions are coming into the intracellular fluid. So if we look on the outside, as the sodium ions enter into the cell through their chemical driving force, the outside of the cell is going to be losing positively charged sodium ions, and the number of negatively charged ions proportionately is going to begin to rise compared to the number of positively charged ions. So what's going to happen to the outside of the cell? It's going to begin to become negative. So look at this. Electrical driving forces are developing. As sodium enters into the cell, it's making the interior of the cell more positive. And as sodium enters into the cell and makes the interior more positive, it's making the exterior more negative because the exterior is losing positively charged sodium ions. So what overall effect are these electrical driving forces going to have on sodium? All right. Sodium is entering in through its chemical driving force because we've made the cell leaky to sodium. Put a bunch of integral proteins, pores for sodium into the cell membrane. Sodium's entering in, making the interior positive, making the exterior negative. All right, so what we can do is we can probe the cell again and look at how positive or negative it becomes, in this case positive. First things first, we know that the inside is going to become more and more positive as more and more sodium enters into the cell, and the exterior is going to become more and more negative as more and more sodium ions are lost. All right. What that means is the exterior is going to develop this negative electrical driving force, and we know that negative electrical driving forces, what do? They pull positively charged ions towards them. And so as the exterior, becomes more and more negative, what's going to happen is the exterior is developing a negative electrical driving force, and it's going to begin to pull sodium backwards. What this really means is as the exterior becomes more and more negative, it's going to slow down the rate at which sodium enters into the cell through its chemical driving force. And here's what we know. Once the interior of the cell hits about positive 60 millivolts, sodium has reached what's known, as we have discussed now, its equilibrium potential. What that means is, once the inside of the cell is positive 60 millivolts, the exterior is negative enough, probably right around negative 60 millivolts, although the extracellular fluid is rather difficult to measure. The exterior has become negative enough, developed a strong enough negative electrical driving force to pull the sodium ions backwards through a negative electrical driving force at the same rate and drive that they want to come in to the cell through their chemical driving force. So let's just recap that real quickly. What do we want to know? Sodium's equilibrium potential. We know that it's high on the outside to begin with. We know that it's low on the inside. We know that there are no electrical driving forces to start inside or outside of the cell in the intra or extracellular fluid. Okay, so we make the cell permeable to sodium at some leak channels into the membrane, and now sodium can come in through its chemical driving force, its diffusion gradient, and as the sodium comes in, it makes the interior positive and it makes the exterior negative. And what that really means is that the exterior is now developing a negative electrical driving force, which is pulling the sodium ions backwards. All right, once enough sodium enters into the cell to make the inside of the cell positive 60 millivolts, we've reached sodium's equilibrium potential. Again, what that means is once the interior has hit positive 60 millivolts, the exterior is negative enough, has developed a strong enough negative electrical driving force, that the drive for sodium to come in through its chemical driving force equals the drive for sodium to go back out through its electrical driving force. So there will be no net influx of sodium ions at this point. Right? Because the chemical driving force for sodium to enter equals the electrical driving force for sodium to leave. Right? So we get stuck at positive 60 millivolts. If we wanted to become any more positive, we would need sodium ions. We would need a net influx of sodium ions. We would need, more sodium ions to keep coming in than are leaving. And that's not going to happen once we get to positive 60 millivolts because the drive for sodium to come in equals the drive for sodium to go out. No matter the ion, you can isolate any particular ion and you can figure out its equilibrium potential. Its equilibrium potential 100% of the time is going to be once the inside of the cell has become positive or negative enough so that the electrical and chemical driving forces equal one another. And that particular ion at that point, there's going to be no net efflux or influx of that ion once we hit the equilibrium potential.
So that concludes our discussion of the equilibrium potentials for sodium and potassium with regard to neurons. I've said this in the past, but I'll say it again. I say with regard to neurons because the equilibrium potential for sodium and potassium within other cell types would be a little bit different. On a functional level, you would figure it out in exactly the same way. However, for instance, if you looked inside of a muscle fiber, the concentration of potassium on the inside versus the outside may be just a little bit different. Right? There may be a little bit more potassium or a little bit less potassium on the inside of a muscle fiber compared to a neuron. And that then would influence potassium's equilibrium potential. It's always going to be higher on the inside versus the outside of whatever the cell type is, but the exact concentrations on the inside versus the outside for potassium or for sodium is going to be a little different from cell to cell, which would mean that the equilibrium potential could be a little bit different. It may be negative 80 millivolts for potassium inside of one particular cell rather than negative 94 like it is for neurons. But I just want you to be sure this information is applicable to all cells in the human body, not just neurons, even if the number would be a little different. I also want to say that there are more ions than just sodium and potassium. For example, calcium and chloride are also very important ions as well. They have equilibrium potentials with regard to neurons as well. And in a little bit more of an advanced conversation, you would want to know the equilibrium potential for those ions as well in order to be able to factor them in to the resting membrane potential. But for the sake of this lecture, we will only focus on sodium and potassium because they're the most important two ions. So let's go ahead and use our knowledge of sodium and potassium's equilibrium potential with regard to neurons to determine the resting membrane potential.
All right, so you have this hypothetical cell here. You know that on the inside there's the same number of positive and negatively charged ions. So the inside of the cell is neutral. You know this is true for the outside too. There's the same number of positive and negatively charged ions on the outside, so there's no charge on the outside. The outside, the extracellular fluid, is neutral. Now, after everything that we just discussed, hopefully you know that potassium is high on the inside and low on the outside. And you know that sodium is high on the outside and it's low on the inside. Okay? So there are chemical driving forces that do exist, but no electrical driving forces that exist to start off with. You know that potassium wants to leave through its chemical driving force, and you know that sodium wants to come in through its chemical driving force. So what's going to happen? Well, the first thing that you have to recognize is this varies a lot from one cell type to the next. But basically every cell in your body is more permeable to potassium than it is to sodium. What does that mean?
It means that if you look at any cell in the human body and you look at its plasma membrane, you're going to find many more leak channels for potassium than you will find for sodium. As I have said, this varies from one cell to the next, but since we're focusing on neurons, within a neuron, this estimate varies a little bit, but neurons are at least 20 times more permeable to potassium than they are to sodium, perhaps more than that. So of all of these leak channels that I have drawn, perhaps one of them might be for sodium. Every other one of these leak channels in the plasma membrane, if we're talking about a neuron here, would be for potassium. So again, within this neuron, there's at least 20 times more leak channels for potassium than for sodium. And what is this going to translate into? Well, we know that to start off with, potassium wants to leave and sodium wants to come in to the cell, to the neuron. And we also know that there's no electrical driving forces to start. There are only chemical driving forces. And now we can see that within this neuron, there's at least 20 times more leak channels for potassium to leave through than there is sodium to come in through. So I always do this, but imagine you have two balloons filled up with the two balloons are the exact same size, filled up with the same amount of water. One balloon has had 25 holes poked into it. The other balloon has had one hole poked into it. And then you ask, well, which balloon is going to drain faster? Right? Assuming the holes are of the same diameter, of course the balloon that has 25 holes in it is going to drain much faster than the balloon that has one hole within it. Right? The rate at which water is leaving the balloon with 25 holes in it is much greater than the rate at which water is leaving the balloon with one hole in it. So if you have a plasma membrane like this that has at least 20 times more potassium leak channels within its plasma membrane than sodium leak channels within its plasma membrane, then potassium is going to be able to leave the cell at a much greater rate than sodium is going to be able to come in, right? Potassium is going to leave through all of these different leak channels, while sodium can only come in this drawing through this one leak channel. So even if the chemical driving forces, let's say for potassium to leave and for sodium to come in, were essentially the same, if potassium has many, many more channels, leak channels that it can leave through than sodium has channels that it can come in through, then the rate at which potassium is going to be able to leave the cell is significantly greater than the rate at which sodium is going to be able to come in. So when we talk about a cell developing or its resting membrane potential developing, one of the things that we have to recognize during that development is that potassium is going to exit that cell much greater at a much greater rate than sodium is going to enter that cell, thanks to the fact that the cell is much more permeable to potassium than to sodium, has many more leak channels for potassium than for sodium.
So here's where we're at. Potassium is leaving at a greater rate than sodium is coming in. And this is all due to permeability. The cell is more permeable, has more leak channels, integral proteins, for potassium than it does for sodium. So potassium is able to leave at a greater rate than sodium is able to enter. So what does that mean for the inside? We know that to start off with, there's the same number of positively and negatively charged ions on the inside. Okay, if more potassium ions, which are positively charged, are leaving than sodium ions are coming in, which are positively charged, then in net terms, the cell is losing more positively charged ions. It's losing more potassium, positively charged potassium ions, than it's gaining in positively charged sodium ions. So in net terms, again, the cell is losing positively charged ions. And the proportion of negatively charged ions on the inside is now rising compared to the number of positively charged ions. So what's going to happen? As more and more potassium leaves compared to sodium coming in, the cell is going to be losing positively charged ions, and the inside is now going to begin to develop a negative charge. The number of negatively charged ions on the inside is going to begin to become greater than the number of positively charged ions on the inside, and we are developing this negative electrical driving force that exists on the interior. And this is going to become more and more significant as more and more potassium ions leave compared to sodium ions coming in. But in the meantime, let's talk about what a negative electrical driving force developing means. Okay? So as the interior becomes more and more and more negative, what effect is that going to have on potassium? Well, if the inside is becoming negative and a negative electrical driving force is developing, that's going to pull potassium backwards, and it's going to decrease the rate at which potassium can leave through its chemical driving force. What about for sodium? As the inside becomes more and more negative, sodium is a positively charged ion. Okay? So as the interior becomes more and more negative, and the stronger negative electrical driving force develops due to more potassium leaving than sodium coming in, that stronger negative electrical driving force is going to begin to pull sodium in at a greater rate. Right? It's not going to change the number of leak channels that exist for sodium, but if the inside becomes more and more negative, now sodium doesn't just have a chemical driving force to enter, right? High on the inside, low on the inside. High on the outside, low on the inside. It also has an electrical driving force to come in. Right? It has a chemical driving force to come in, and now it also has this electrical driving force pulling it in. So as the interior becomes more and more negative, let's think about potassium and sodium together. As the interior becomes more and more negative, this negative electrical driving force develops. It's going to slow down the rate at which potassium can leave. It's going to, slow down the rate at which potassium can leave through its chemical driving force by being pulled back through the electrical driving force, and it's going to increase the rate at which sodium comes in. because now sodium's not just coming in through a chemical driving force, sodium's also being pulled in through this negative electrical driving force.
So let's go ahead and put all of this together and see how it results in the resting membrane potential being developed, specifically with regard to neurons. So we know what's happening right now, right? The inside has become more and more negative. Why? Because potassium is leaving at a greater rate than sodium is coming in, right? That's made the interior negative because the cell's losing more positively charged ions than it's gaining, and by consequence, that negative electrical driving force that's developing is pulling potassium ions backwards, slowing down the rate that potassium ions can leave, and that negative electrical driving force is pulling the sodium ions inward to a greater degree and increasing the rate at which sodium can enter. So this will just keep happening, right? As more potassium leaves than sodium enters, the inside will just get more and more and more negative and continuously slow down the rate at which potassium can leave and increase the rate at which sodium can come in. And eventually, you will get to what's known as the resting membrane potential. In the case of neurons, that happens around -70 millivolts. At -70 millivolts, the neuron's membrane potential rests, which is where the resting membrane potential term comes from. What that means is at -70 millivolts, the rate at which potassium is leaving equals the rate at which sodium is coming in. Basically, the inside of the neuron has become negative enough that it is pulling potassium backwards to such a degree and pulling sodium in to such a degree that potassium is actually leaving the cell at the exact same rate that sodium is entering. And if potassium is leaving the cell at the same rate that sodium is entering, then the cell is no longer losing more positively charged ions than it's gaining. Right? It's losing just as many positively charged ions as it is gaining. Just as much potassium is leaving the cell, potassium is a positively charged ion, as sodium is coming into the cell, sodium is a positively charged ion. So, since the cell is losing just as many positively charged ions as it is gaining, the membrane potential is not going to change anymore, right? It's going to be stuck at -70 millivolts. If you wanted to make the membrane potential more negative, for example, you would need potassium to keep leaving the cell at a greater rate than sodium was coming in, because then the cell would continuously lose more positively charged ions than it was gaining, and that would allow for it to become more negative. But if you get to a point where the cell is losing just as many positively charged ions as it is gaining, then the membrane potential is not going to change anymore. It's going to rest at that particular value. And in the case of neurons, that is -70 millivolts. This principle is true for every cell in the human body. Once the inside of the cell has developed a negative enough electrical driving force, so that just as many positively charged ions are leaving the cell as positively charged ions are entering the cell, that is when the cell reaches its resting membrane potential. This principle is always the same. It can be a little bit more confusing, only mildly more confusing, when you throw in different potassium and sodium permeabilities, and when you factor in calcium and chloride, which you do have to do in more advanced discussions. But I promise you, when you apply these exact same principles to that, figuring out the resting membrane potentials of other cells and why they're slightly different is incredibly easy. And I do have another video that does that. But for now, let's keep focusing on neurons and why the resting membrane potential is -70 and how it's possible for that resting membrane potential to be stuck and stay or rest at -70, because there's a little bit more to it.
If you think about this, though, there's a problem that exists. Yes, potassium is leaving at the same rate that sodium is coming in, once we're at negative 70 millivolts. But at negative 70 millivolts, potassium's still leaving and sodium's coming in. It's just that potassium's leaving at the same rate that sodium is entering. But if this were to continue on indefinitely, the cell would just keep losing more and more potassium, and it would keep gaining more and more sodium. The cell always needs to have high potassium on the inside, low potassium on the outside. It always needs to have high sodium on the outside. Ooh, that's bad. And low sodium on the inside. Okay. And if it just keeps losing more and more potassium ions and gaining more and more sodium ions, it's going to completely throw this whole thing off. Eventually, there's not going to be a higher concentration of potassium on the inside compared to the outside if potassium keeps leaving, and there's not going to be a lower concentration of sodium on the inside compared to the outside if sodium keeps entering. So how can we possibly resolve this issue so that the concentrations of potassium and sodium on the inside and the outside don't get completely thrown off? The answer is relatively simple. Embedded in the plasma membrane of all of our cells are sodium-potassium pumps. What do sodium-potassium pumps do? Sodium-potassium pumps are a type of primary active transport. They utilize ATP to pump molecules from an area of low to high concentration. And specifically, what the sodium-potassium pumps do is they take sodium on the inside where it's low and pump sodium to the outside where the concentration is high. And the sodium-potassium pumps simultaneously pump potassium, the outside where the concentration is low, to the inside where the concentration is high. So the job of the sodium-potassium pumps, this primary active transport, is to continuously kick sodium out and kick potassium back in. So what does the sodium-potassium pump actually accomplish here? What the sodium-potassium pump accomplishes is, well, if you're constantly kicking potassium back in against its concentration gradient, you're going to keep potassium levels high on the inside and low on the outside. And if you're constantly kicking sodium out, right, and moving it from a low concentration on the inside to a high concentration on the outside, you're going to keep sodium levels high on the outside and low on the inside. So the sodium-potassium pumps allow the cell to maintain the concentrations of sodium and potassium on the inside and the outside indefinitely. Right? And as long as sodium stays high on the outside and low on the inside, and potassium stays high on the inside, low on the outside, then the resting membrane potential of negative 70 millivolts can be maintained indefinitely. Right? Because as long as those concentrations are there, then we can rest at negative 70 millivolts for an indefinite amount of time. The real problem would be if this, concentrations of potassium and sodium on the inside and the outside were to get thrown off through potassium continuously leaving and through sodium continuously coming in. The cell resolves that issue by constantly kicking that sodium that comes in right back out and kicking that potassium that's leaving right back in.
One last thing that I'll point out with this as well, with regard to the sodium-potassium pumps, is that everybody knows that the mitochondria makes ATP and that the ATP is utilized throughout the cell for survival. But I think much of the time people miss where ATP is actually truly consumed. And a huge portion of ATP is actually consumed by these sodium-potassium pumps. This is actually the main location where neurons consume ATP. It's via their sodium-potassium pumps to continuously kick sodium back out against its concentration gradient and continuously kick potassium in against its concentration gradient. You need ATP to do that. And it's essential that this keep happening in order for the concentrations of potassium and sodium to stay the same on the inside so that the membrane potential can stay the same and so that the neuron can generate action potentials, which is its function. So I just wanted to make a point that in terms of our body, a lot of ATP is consumed by the cells of our body simply through these sodium-potassium pumps, because it is essential that our cells maintain these resting membrane potentials. So what we did in this lecture was we looked at how resting membrane potentials are established. And even more specifically, we looked at the resting membrane potentials specifically of neurons. So when you look at a neuron like this, the resting membrane potential of negative 70 millivolts would be everywhere throughout the neuron, right? Throughout the dendrites, throughout the cell body, throughout the hillock, throughout the axon terminals, into the buttons. And this is going to be fundamental to the way that neurons generate action potentials, and of course then are able to function. So if every single one of these regions is negative 70 millivolts, what must that mean? It means that within the plasma membrane of every single one of these regions, there are a whole bunch of potassium leak channels and a lot less sodium leak channels. And that means potassium is leaving those regions at a greater rate than sodium is coming in, which is causing the interior to become negative until it reaches negative 70 millivolts. And then when the interior reaches negative 70 millivolts, there's a strong enough negative electrical driving force that it pulls potassium backwards to such a degree and sodium inwards to such a degree that potassium leaves at the same rate that sodium comes in, and then that region rests at negative 70. And additionally, throughout all these regions, in order to maintain those concentrations of sodium and potassium, that means that there are sodium-potassium pumps embedded throughout the plasma membrane of the entire neuron as well, to continuously kick the potassium back in and the sodium back out. And this would be true for any cell that has a resting membrane potential, which most cells in the human body do. It's just that the resting membrane potential may be slightly different in terms of a voltage, right, a value from one cell to the next. If you're curious how there are these small differences in the membrane potential from one cell to the next, or if you're curious how cells like neurons utilize their resting membrane potentials to generate action potentials, then please consider watching one of the two videos on the screen. Additionally, if there's other content you'd like to see, other concepts covered, please let me know.